Okay, so today we're going to transition from server-side stuff more towards client-side issues. And what we're going to start with is cross-site scripting, which is A7 on the OWASP top 10. This is otherwise known, in fact, I think it's better to refer this more as JavaScript injection, but cross-site scripting is what you'll commonly see. It's pretty prevalent. So here is a graph, this is a couple years old, of the number of domains that they have scanned and found that might be vulnerable to this kind of exploitation. But in order to talk about cross-site scripting, I have to talk about how the browser implements JavaScript security. So we've talked about JavaScript as something that you download from a site, and it's actually executing code on behalf of that site. Well, code execution should not be taken lightly. And so one of the issues with loading a page is that a lot of times the page is getting content from multiple places. And the issue is when you get multiple scripts and objects from different sites, they're all interacting in the same page, the same DOM. So the DOM is referred to as a document object model. But basically a web page has all these different scripts and all these different web objects that are coming from different sources. The problem is that these sources could either be benign or malicious, right? You don't know a priori the intent of the content provider shipping you stuff, okay? One of the classic examples are banner ads. So if I buy some imprints on an ad network, and then as part of delivering you a banner ad, I deliver you some JavaScript code that tries to steal a whole bunch of other stuff on the page that you're on. It tries to figure out what you're on, tries to dump all the data on the page that you're on. That's something that you know, up front, you're like, oh, yeah, that should be possible, right? They're delivering me code and it's executing on my page. Okay, so the problem is that all of this content shares the same page context. And what you want to do is prevent any malicious content. Now, again, you don't really know the intent of any content that you're downloading. You want to prevent malicious content from stealing or modifying the page content, so it shouldn't be able to, on the page that you're on, be able to transmit the cookie of that page. So if I go to Gmail and somebody has put a banner ad in there, they shouldn't be able to steal my Gmail cookie, even though it's sitting there on the same page. Likewise, they shouldn't be able to overwrite UI elements on Gmail to trick me into clicking stuff. That should be disallowed as well. So here's a scenario that's in this book, Web Application Security book, A Beginner's Guide, where they imagine a world without client-side security. And this is something that could happen if we hadn't thought about security and JavaScript execution. You could have a flower shop placing a banner ad into AdWords, and then when you as a victim go to a site that hosts that shows that banner ad, the ad could send you a script that executes on your browser to retrieve your Google Calendar using your Google cookie, assuming that you're on a Google site, to download any of the birthdays that you have on your calendar, and then of course it'll find that, oh yeah, mom's birthday is coming up. Then it wants to check your email. So maybe Yahoo or Hotmail. And if you're logged into either of these two, then it will try and get the access to your mail using your cookies. And then checks your mail to see what kind of flowers your mom might like. Wants to figure out how much money you have in the bank. So maybe it retrieves some bank balance to figure out your balance. And so if you have a lot in your balance, you could price out a more expensive bouquet. And then finally, it uses this information to display you personalized offers. Okay? So that is where this should make you feel uncomfortable executing JavaScript. Do you have a question? They could, but if they did, they'd be in some serious trouble. So we'll get to, we'll talk a little bit about that in a second. Okay, so the issue here is that when you access a malicious site, or if you're going to a malicious site that's got hosting you a banner, for example, the issue is that it could, a script running on that site might be able to source a request to a legitimate site, and if you are logged into that legitimate site, that request will happen with your authenticated cookie on that page. It'd be like, oh, you went to attacker.org, but I'm going to make this AJAX request to email.com. Hopefully you're logged in. I'm going to retrieve whatever content is there. Okay. What would you do to stop this? What does the browser do? If you haven't peeked through the slides already, what would you do? Yeah. There is a cookie policy. Yeah, that's one of the things you would do. Something more generic than just your cookie, though. We'll see that you need a broader solution. Session. Yeah, you're going to apply this policy to sessions. Basically, what is done on the web browser is this idea of a same origin policy. So as soon as this came up on the radar, this ended up being a browser's approach for locking this kind of access down. It's explicitly denied, and the way it's denied is through the same origin policy. So you restrict a script's ability to navigate to other sites or view content delivered from other sites unless the page that you're accessing, the server you're accessing, or the content you're accessing has the exact same origin as you. Okay? So this prevents you from being able to access other kinds of content outside of your domain. The origin in the same origin policy is defined based on the protocol. So these are two different protocols, so they wouldn't be the same origin. Different ports. So the protocol, port, and host are how the same origin is defined. All three have to match in order for you to be considered accessing something from the same origin. So if you're using different protocol numbers or port numbers, it's different domain names. It could even be a subdomain, and those would be classified as different origins. Okay, so those are the three things that are used to specify the origin. And again, this is enforced at the browser to keep sites from accessing each other's content. So if you're including scripts from multiple different places, they're only able to make requests back to those origins and access content from those origins, is the idea. Okay, so in that previous scenario, the same origin policy will deny this request because this page is attempting to access content from a different host. So the port matches, the protocol matches, the port matches, but the host doesn't match. So it would be denied by your browser on the client side. All right, questions about the same origin policy? Yeah. Yeah, it could. Yeah, you could. Yeah, man-in-the-middle attacks on some of these things have happened. But yeah, it's assuming that, we'll get into that in a bit, but yes. Okay, so applying the same origin policy, say that you have a page where you've downloaded some things from this site, www.flickr.cxx. All of these URLs would be denied in the same origin policy. So the first one would be denied because the port doesn't match, or the protocol doesn't match. I initially went to HTTP, and I'm trying to get access to something over HTTPS. This access would be not denied because the protocol doesn't match. Here's another one, photos.cxx. This would be denied because the host doesn't match. This one, my.flickr.cxx, it's a subdomain. This would be denied because the host doesn't match. Flickr.cxx is the same. So again, this is a subdomain. That doesn't match. This doesn't match as well for the same reason. You could go to the same site but a different port, and this would be denied because that doesn't match. And then finally, you have an access here, www.flickr.cxx. It matches the port. It matches the host. This would be allowed. Okay? Just as examples of same origin policy being applied. Okay, so the problem with the same origin policy is that things like web mashups are difficult to implement. So if you have a page that is intentionally aggregating content from other sites' pages, you have a problem. It used to be that you went to an aggregator and it would render you like if you have like an email aggregator. Like, I don't want to go to the dozen different email addresses I have on the web. Maybe I can have a single page that gives me views onto all of my inboxes. This is much more difficult to do with the same origin policy. And as a result, we have a lot of exceptions to the same origin policy. So this is where the security issue comes in. The first exception is the script tag itself. And so you are allowed, using the script tag, to specify the inclusion of a script from another domain. So we explicitly allow you to load JavaScript libraries from other domains. And this is really important, especially if you're taking the full stack web course. It's like, yeah, I have to be able to include like client-side frameworks and these sorts of things from other places, fonts maybe from Google. Like, I got to be able to download other content that I don't want to host myself. And I am going to trust those folks to give me a good script. Okay, so hopefully it doesn't get hijacked or spoofed, that kind of thing. But I need the browser to allow me to do this. So when I go to pdx.edu and it delivers me a script that says, oh, use this JavaScript hosted on Google, it should allow that. Okay, the content provider is explicitly saying to the browser, get that script. Okay. So yeah, all of the popular JavaScript libraries, jQuery, React, and Bootstrap, you can pull those libraries straight from the source using the script tag. Obviously, you can make a local copy as well and refer to the local one, but then you're forced to like make sure that that local copy is updated. Okay. So the issue with this is that if you have decided to include that code, if that code you included was actually malicious, then it looks like you're at fault, right? Because it's coming from you via this thing. The other thing is that with this exception, you can only include pointers to valid JavaScript code. So the content that you pull in with the script tag is validated to be legitimate JavaScript before you're allowed to include it. And we'll talk about why that matters in a second. In fact, we'll talk about it in the next slide. So one of the things that they wanted to do was to start delivering data cross-domain. And so the origins of the JSON format was to get around this, to get around the fact that you had to include valid JavaScript code in order to do this thing cross-domain. So they decided they wanted a data format that looked like valid JavaScript code. And that's what the JSON object notation is. And so this solves that problem by creating a data format that is also valid JavaScript code. So this is a format that is valid JavaScript, and then you would be able to get this to pass through that filter. And so you would serialize this as a string and transmit it, and then on the other side, this would pass the JavaScript code test. Okay. Another exception is the iframe. This allows a page to force loading of a view of another page within your site's context, potentially. We'll talk about restrictions on iframes. So if you're attacker.org, you could say, oh, put a little window on the page that's for google.com. And even though you're on attacker.org, you've got an iframe that's hosting content from Google. That's what this allows you to do. create another page within your, another frame that views another page within your page's context. So here's an example. If you're on attacker.org and it says, I want to create an iframe of a particular 300 by 300 view of this site.cxx home.html, and I want to have that as a small window inside of my base page. That's the iframe. Okay, one of the restrictions on iframes, so this could be very dangerous. One of the restrictions on iframes is that it can't share any of the content with that base page. It locks that down. Well, it locks it down based on the same origin policy. Okay. Another thing that is allowed is that you can change your origin in JavaScript, but you can only change it in a particular direction. Like if you are a subdomain, you can change your domain to the higher level domain. So if you have, you know, a.foo.com and b.foo.com, but you want them to actually share content with each other to be considered the same origin, then you can lower both of the sites to foo.com, and then they can share the same domain. Okay? And this is how you might do this. Another one is cross-origin resource sharing. And I have an explicit section on this, but this is another way of opening up the same origin policy because it's too restrictive for you. Okay, one of the things I want to talk about with cross-sites, the same origin policy, is that we have two notions of origin now. Someone just brought up cookie origins, and I have just explained to you the same origin when it applies to JavaScript. Turns out their notions of origins are different. And so you can run into trouble applying the one origin policy towards the other, thinking that they have the same model. They're not completely different, but they are different. So the differences are here. So these two things aren't the same. Your cookie origin and your JavaScript origin aren't the same. The cookies only care about the name, the DNS name, but they don't care about the port number or the protocol you're using. Those cookies have the same sort of scope, whether you're using port 80 or port 8080, whether you're using HTTP or HTTPS. In addition, for cookies, you can actually target a specific URI path that a cookie is valid for. You can target subpaths of a tree with your cookie. You can't do that with the JavaScript origin. Okay, so now, given that we have some understanding of JavaScript security, I'm going to talk about cross-site scripting, which is the vulnerability. So the idea here is that you're targeting the client instead of the server. The idea is that you're going to inject rogue data into legitimate pages or within links that is delivered to the client and executed. So you're trying to trick the client into executing JavaScript code that you're delivering to them. And if you look at this pattern, this is again mixing code and data together. You're shipping data that's got like embedded code in it that the client is tricked into executing. And anytime you have these data formats that mix both side by side, like you do in HTML, this is where your problem comes in. Here's an example of cross-site scripting, a vulnerability. So if you search for the term banana cream pie recipe, you'll go to a search engine, and it used to be that the search engine would tell you, oh, your search for banana cream pie recipe found a certain number of results. Okay, and then you're like, okay, that seems interesting. If you did something like this, I'm going to search for the term, and this is the HTML tag for italics. If I search for this, what do you want the output page to contain? Do you want it to contain your search for the text, the I tag banana cream pie, and I tag found a certain number of results, or do you want this, your search for italicized banana cream pie recipe found a certain number of results? Which one do you think is the thing you want, like as a security person? The first one or the second one? The first one. So if you think about it, which site is treating your data, which is the search term, as code? As it turns out, this this site is treating the data that you are including as the search term as code and being executed. So what would this do if you delivered it to a vulnerable browser in a banner advertisement? Say you inject into the banner ad a script that sets the document location to this with the cookie. What do you think that might do? What was that? Redirect you to the bad site with, what would you access on the bad site? Do you think that actually exists on the bad site? It wouldn't. It would give you an error. But what does the bad guy have if he, or gal, it should be gender neutral. What would that, if the malicious actor looked at the HTTP logs, what would they find? Your cookie for the page that this has been injected into. Okay. What about this one? So via a phishing attack. So if someone delivers you a rogue link in the email, and this link looks legitimate, it's going to a page, a search engine, but the search engine is basically doing the same thing, this banana cream pie recipe business. What do you think this will do? If you look at that. It'll, again, steal your cookie if the user clicks on that. But the user might click on it because if they hover over that link, it's like, oh, yeah, that's a legitimate site that I would, this might be google.com, I'll click on that. But if google.com, anywhere in Google's site, if they have a single page that is vulnerable to this kind of attack, then that single page will emit your Google cookie to the bad guy. Well, this is gendered as a bad guy, so I can say bad guy without getting into issues. Okay, so another thing that you could do if you're really sneaky is to use a URL shortener to hide the payload on the hover, right? Like if you don't want to see, because eventually this you'll see embedded in the link, you'll see some JavaScript code that looks gnarly, and then hopefully that will stop you. But if you don't want even that to show up, you might use a URL shortener and say, hey, here's the bit.ly link. Or here's the, well, Google shut theirs down. They shut theirs down because of this stuff. So you'll see that there's some papers on this, on the statistics on how many, what percentage of shortened links are malicious, and it's a huge amount. Because obfuscating bad links, malicious links, is something that's very useful for an adversary. Okay. So think about that before you click on a shortened link next time you see one. Okay. There are multiple types of cross-site scripting attacks. I'm going to go over 3, but there's actually other ones. The main 3, the first one is what's called a reflected, non-persistent cross-site scripting attack. This is the most common that you'll find. The idea here is that the data provided by the web client is consumed by the server and immediately reflected back to the client. So this is the banana cream pie recipe thing. As the search term, so you can see that it's either the form field or URL parameter. You're parsing user input and then including that user input as output of a subsequent page. And if that user input has HTML tags in it, it gets echoed back into the resulting page. That's called a reflected attack because you're bouncing it off the server and delivering it back to the client. Okay? And so you would do things like embed that in links that get bounced off of the server. Okay, and so the server just blindly does this rather than trying to sanitize any of the user inputs to strip away any of those fields that might actually inject scripts. One common pattern is that a page takes a username and a password, and then upon failure, the page outputs that that username with that password is invalid. And so in red is the malicious U. So you can set this U to some JavaScript, you know, alert XSS, which will just pop up So this is the way in JavaScript to pop up a window, and that's what this particular thing does. So if you start copying and pasting this payload in all sorts of web forms, and you see which ones will actually pop up a window, you can detect almost immediately whether or not a site has this vulnerability hosted in it. So either of these two payloads, if it actually pops up a window, means that that username password app has got a cross-site scripting vulnerability built in. Okay. The other kind is, the second kind is a stored or a persistent cross-site scripting vulnerability. This is pretty devastating if it happens because the attack persists. I don't necessarily have to get a user to click a link to reflect the malicious script in order to cause it to happen. So the idea here is that the data provided by the attacker is somehow stored in the vulnerable site, and then when legitimate users access that site, it'll be delivered to them. Okay? So one of the famous things that can be done in this, with this one is the watering hole attack, where say you're targeting a company, and that company has a sort of an internal server that everyone goes to for accessing this, that, and the other on the internet. If you can inject one of these cross-site scripts into that server, then all of these employees, that's their watering hole for their information, and then you can get these scripts executing on all of these people. So say it's a bulletin board that everyone looks at in the morning, and these forum posts on this bulletin board are stored in a database. If the adversary uploads a post, a rogue post that's got malicious HTML that includes this JavaScript code, then even though the bulletin board is expecting just data to be given, malicious JavaScript is instead injected into the database, and then the victims that are viewing the forum post will actually execute that JavaScript in their page context. Okay? So you'll see that this pattern is very similar to what we were doing with SQL injection. That's why I put this in with the other injections, because this is injection, but just done on the client instead of on the server backend. Okay, here's I have a couple animations for the stored one. So you have the adversary over here. It's got a browser, finds an application with this stored vulnerability, updates the profile. So the attacker has a profile on that app and wants to hijack any of the users viewing the profile. Enters a malicious script for their profile information and stores that as data on the server. And then when the victim views the page, sees as part of this the malicious script and then executes the malicious script. Is looking to view the profile, but is then delivered a malicious script that executes in the page's context. And then the script runs inside of the victim's browser with full access to the DOM and whatever cookies that page has. And then, for example, can silently send the session cookie, just like we had earlier, tried to send the session cookie to a malicious site. So this could be bank.com, well, not bank.com, like maybe a social media site. And then this allows you to get the session cookie of that person in a social media, on that social media site. This is a good video of showing Facebook every once in a while has this pop up. Hopefully not anymore. I don't know how old that video is, but you can click on that link and there's a walkthrough of how they were able to get this to work on Facebook. Okay, here is a more detailed example. You have a server with a database. The malicious actor will inject as a comment the malicious script. So the text of the comment is basically HTML that executes a script. After submitting this to the web form, this gets inserted as a comment into the backend database that implements the forum. That's now stored on the database. The innocent victim accesses the server. As part of viewing the comments, the server does a select on all of the elements and then includes the results in the resulting HTML. And then as part of the resulting HTML, it expected this to be all text, but because it's got these script tags in it, this will actually, in the page's context, execute whatever JavaScript is there. Okay. Questions about the stored cross-site scripting attack? Okay, the third one is this DOM-based cross-site scripting, where the payload is executed dynamically in client-side JavaScript. JavaScript has the ability to produce HTML DOM elements as the page is executing, and so the idea is to inject yourself in the production of those DOM elements to inject your malicious scripts. So this is where this term comes from. I think the best thing to do is to give you an example. So here is some client-side JavaScript code that will parse a color parameter in the URL. So here is the color parameter, pink, to set the background color of the search results. And so this is the JavaScript that generates the background color. And you can see as part of this, you will do a document write of the body, the beginning parts of the body tag. And then you will pull from the parameters the substring that will give you the last bit of this URL. And then you will write, document.write, the style as the background color of whatever color you have parsed out. And then you will close the body tag. And so when you execute this, so if you click on, or if you access this URL and it executes this JavaScript as part of its rendering, you should get this. Okay? This is the intent of what that script has been implemented. But if you are a malicious actor, you can send this phishing link to the user and then have the user click on this. You include the search engine URL, and then rather than specifying a color, what you're going to do is you're going to terminate the body tag, which is what this double quote and the greater than character do. And then you're going to, since you have broken out of that tag, now you can inject arbitrary JavaScript. And so in this case, you're opening badguy.cxx with the document cookie. Okay? And then because you have broken the body tag, you have to, so at the end of this script, you have to sort of consume the other side of that tag in this script. So that's what this thing does. And so what this will produce on the page is this. So terminates the body tag, injects the script, and then injects some garbage to consume the other parts of this. So this double quote and this greater than have to be matched up. And so this is what the span A is equal to quote, double quote B at the end of this is for. Yes? No, like if you didn't do this, maybe the browser would still try and run. But you might get, the browser might cough this up if you didn't sanitize it. You could also put some comments in here maybe. No, you wouldn't be able to. This would be something that you would want to fix up the, well, I mean, you would have multiple chances at this. Like you could debug, like this is a public site, so you could actually go back and forth and see the syntax that you get back on this one, yeah. Any other questions about how this particular attack, anytime you're generating HTML, then that code that's generating that HTML is injectable, potentially injectable. So that's an example. Okay, so what do you do after code injection? Well, you have full access to the JavaScript engine if you can inject arbitrary JavaScript. So we have talked about stealing a user's session or authorization cookie. That's the most common target for this kind of attack. But you could do other things. You could rewrite the web page via the DOM to deface any website. So if you want to say hacked by Russians, you can just change the page inner HTML to basically, I mean, basically a denial of service attack on the hosting provider by replacing all of the HTML with that. You can open a bunch of new windows. So you could just call window.open and open 100 windows on the client. You could redirect a user to a phishing site. So send a redirect to have the user go elsewhere. Basically hijacking the browser is what this is doing. You can try and inject fake login elements. So tampering with the page content to trick a user into entering the credentials. Using these parts, you could do inject iframes. You could do some, element injection using this, etc. You could create worms. So here is an infamous Myspace worm, and this was a post that as soon as it was posted the first time, this thing spread everywhere. So it fits within the character limit of a tweet. So how did this work? Well, if you looked at this script, and again, it's using a cross-site scripting vulnerability. The first part of this script defines a script with the class, and this class allows you to get a handle on the DOM. So it allows you to get a handle through jQuery. So this syntax, if you haven't taken the full stack course, this is the way jQuery has this tree model that you can access different elements of the HTML DOM using this model. So in this case, you want to figure out where in this HTML tree you are. And so that's what this script basically finds a handle to itself. And then what it does, it knows it's over here. Then what it does is the second part is it tries to get into the enclosing tweet. So it finds its parents, and then it finds all the links in the parent. And if you look at the links in the parent, there are these replies, there's the retweets, there are the likes. And so what it does, if you look at this, is it tries to click on the link that is the retweet link. And so this is what it does, and then it goes ahead and uses JavaScript to click on that link. And so this is how it propagated. Anytime anyone viewed this tweet, you would automatically retweet it. And this brought Twitter down. And this got the guy, I think he's a legit hacker now, but it got him like 9 months or something. Yeah, so this ended up being a Twitter thing for a short time. Okay. Another thing you can do is steal sensitive data via rogue web requests. So if you know you have been embedded into like a bank page, this is why banks hopefully aren't doing banner ads, you could grab different elements in that page. Now, a lot of times these would fail, but if you ended up on a page that had these elements by name, like get element by ID, if it's got these elements in that page's context, then you can basically pull those things out via JavaScript. The last one is you can use these vulnerabilities to inject browser exploits, and this is what the FBI did for their playpen sort of dragnet. Okay, how do you debug XSS? You're going to be doing this for your lab. What you would do is you can start injecting script tags into whatever page is sitting there giving you a form, and then figure out which characters got encoded and which ones did not. And if you see that the less than or the greater than tag did not get stripped out, you immediately know you can inject the script tag. But there are other ways of injecting JavaScript without using the script tag. And so you're going to have to find different ways of executing JavaScript code with your exercises. There is, again, this big list of naughty strings to give you some ideas of things that you can inject. Browsers, I don't know the prevalence of this anymore, but it used to be that browsers would try and filter a lot of cross-site scripting vulnerabilities. But doing this on the client side turned out to be a real hassle. So I know Chrome just got rid of their XSS auditor that no longer ships with the browser. And then finally, there's a funny example. This is one of the funniest cross-site scripting examples that I've come across. This happened over the summer. And this is similar to naming your company a SQL injection. You remember that, where it's like drop companies table? This guy named his Tesla a well-known cross-site scripting payload, and then didn't think anything of it until his Tesla had a crack in the windshield, brought it in for service to get it replaced, and then because this payload used XSS Hunter So what you do is you can create custom XSS payloads to bind your payload to a specific instance. So he had one bound to his Tesla car, and then he got a notification when he sent his Tesla in that this payload had been hit, and then he submitted that back to Tesla and got $10,000. To probably, yeah, that and more. Well, actually, I don't know. I don't have a Tesla. Maybe not. But yeah. Let's see here. Okay, so how do you prevent this thing? On the client, you can just get rid of all scripts. So that's pretty draconian. You'd be very unhappy navigating the web with no JavaScript, but some people do. Another way to do this is server prevention on the input. So if you have a forum, you could strip out all of the JavaScript tags on the input of that form, or you can use forms so a lot of sites allow you to format input. So like, for example, in Slack or any of these sort of markup languages, so that you can actually author content that looks good. So the idea would be to use a formatting input that is different than HTML, so that you have these things completely separate, the HTML tags and the formatting instructions. And so things like wiki text and markdown allow you to accept formatted input that you can render without actually having the opportunity to inject HTML tags. It explicitly gets rid of those from the syntax. And the other side is the output side. You can do this on the server by employing some of these safe escaping schemes for various HTML contexts. So if you are taking data from a database and you want to display it in HTML, you can use any one of these encoding libraries to sanitize the output, so that things like the script tag end up getting changed over to their HTML encoded versions. So the less than and the greater than are HTML encoded, because you know you're going to display that on a page, rather than shipping what you get back from the database directly to the client. So these are things that you can get at a, let's see, this is the Xs library, which is what OWASP has these different ways of, these different encoding libraries on their site. Okay, there are other tools that allow you to do this in the programming language of your choice that you can look at. So these are just some of the tools that people are using to get rid of this from their content. Okay, I'm also going to talk a little bit about cross-site script inclusion. So this is often folded into cross-site scripting, but it's slightly different. So the difference between these two things is in cross-site scripting, the victim is on a legitimate page, and the adversary is trying to inject malicious code for the client to execute. Cross-site script includes the victim is on the malicious page, and the adversary is tricking the victim into pulling the content using the victim's cookie from the legitimate site. So both of these are considered cross-site scripting, which is why I wanted to cover the second one. So here's an example. The attacker page includes script from a legitimate site, and then if the site is, if that content is the content from the legitimate site is retrieved with the site's cookies, you can get personalized information like contacts from that legitimate site, even though the victim hadn't intended to share that content with you. Okay, so here's what it looks like. I go to attacker.org, and within attacker.org, it includes a URI that tries to get my JSON contacts. And because this is actually valid JavaScript, the browser will look at this and say, oh, script source, I don't have to pay attention to the same origin, and this is valid JavaScript, so I'm good. I'll let this happen. And then if this is done with the cookie for Gmail, then in the attacker's page, I might be able to get this. Now it's still, the attacker still has to be able to pull this off of the page. And so as part of this, so you can see that this is a JSON object. And it's a JSON object that's got a bunch of entries in an array. And so as part of this attack, the other thing you would do is overload JavaScript's array constructor in order to actually steal the contacts from the page. And so here the script that is delivered from the attacker has this JavaScript function that would overload the default array constructor in JavaScript, and then this is where your contacts would get exfiltrated in that script. Okay? This has since been fixed, but this is the kind of shenanigans that could be possible. This is the stuff that you have to think about whenever you're doing code execution on a malicious site. Okay, cross-site script includes, so this PayPal exploit, this is the third time it's showed up in this class. It's because that PayPal exploit did a bunch of different things, and one of the things it did was it had to, in order to pilfer the PayPal account of the victim, it had to trick the victim into visiting the attacker page, and then within the attacker page, the victim was accessing, if you look at this URL, the victim is accessing the PayPal reCAPTCHA JavaScript file, and this allows the attacker to now get at the session of PayPal for the victim, and then this allowed the attacker to replay the CAPTCHAs and then subvert the CAPTCHA system, the authentication workflow, to get the credentials in plain text, if you recall how I used it the other two times. So it started with a cross-site script include issue, where the access of this JavaScript was allowed off of the malicious site. Okay. Do you have a question, or? Do these companies have teams that do this? Yes, and you could be one of them, hopefully. But this is just the start, I would imagine. I mean, these things are quite complex, but just conceptually, this is the beginning of it.
Please also remember the ratio of security persons to developers, like 1 to 100, 1 to 150. So, like...
Yeah, so the ratio, yeah, there are teams. The security people are often divorced from the dev teams. Until the last couple of years, people are realizing that's probably not a good idea. So it does help to have both and to not code this, I mean, to be aware of these issues up front. And you'll see a lot of these security prevention mechanisms are being folded into the web application itself. So now you, as a web application writer, need to be able to configure some of the prevention techniques. In fact, a lot of the prevention techniques now are going to be programmatic HTTP response headers, as we'll see when we get to that point. Yeah. Yes, so you will get this a lot. People telling you to bypass security because it impacts their workflow. So if you're a developer, the last thing you want to do is spend a day figuring out how security works. You would much rather turn off security, get it to work, and say, I'm going to come back to that later, but then never come back to it because there's always something else to implement. So that is a thing. Oh, they never said fix it later? Okay, that's even worse. That makes me sad, actually. Ow. I mean, yeah. I mean, so until companies start getting sued for some of the being held liable, which some of these companies are now, like some of the settlements are enormous. They're hundreds of millions of dollars. So yeah, but if you're a small company and you need to actually get that product out there quick, you don't have anything to lose anyway, right? If the thing fails, you're not making money anyway. So if it's insecure, at least if it's a problem, you were successful. So be successful first is a lot of times what the startup has to do. Because anytime you spend on security up front, the venture capitalist is going to be like, that's not useful, right? Like, and then the time to market could end up killing your company anyway. So I'm not going to judge. It just makes me sad that that's what we're doing. Okay. Some of the things you can do to prevent this is strict refer checking upon inclusion of sensitive JSON URLs. So on the Google end, maybe checking the refer to see that it comes from a certain location. The other thing that they do is, this is going to be similar to the CSRF token that we talked about earlier, is to send a random nonce on all of these URLs, only allowing you to retrieve that data from a page that has been previously issued that random number. And in this way, the attacking site doesn't have that random number, tries to access that JSON file without it, and then it says it's denied. So it's the same thing, and we're going to talk about CSRF next class, but already some people have already found the token being sent back and forth. That basically authenticates your session ahead of time without you logging in. It just means that you had accessed the site previously. Okay, so now let's talk about prevention. There are a multitude of things that both prevent this and get around the same origin policy. So these are the three that we're going to talk about. And we'll start with a very concise history of web security, and this actually makes Tacey's comment very prescient. So this is an XKCD cartoon. And so you end up with this problem. I wish these parts would communicate more easily. I wish there wasn't this certificate error. I wish I could just be able to get my content. And then they're like, oh, here's some new technology, makes everything easy, creates arbitrary connections, like turning off security. That makes things really easy. It makes your connections go just like that. And then you're like, oh, no, there's too many connections. It's creating bugs. And security problems, and then the security people are like, aha, we got this new technology that puts these things in sandboxes to make it much harder for you to do the wrong thing, and then you get back to the beginning. So we see this a lot. When the same origin policy was first introduced, it did the thing in the upper left, and then we've been slowly going in a circle to try and say, well, what kinds of access do we want? How do we access it? But, oh, that's too much access. How do we restrict it? And around we go. And so I'll at least do one iteration around this circle as best as I can, because this stuff is going on all the time. So you have to keep up with this. So that's the cartoon, if you want to show it to your manager at some point when you're working. Okay. So the initial goal was to open up the same origin policy and perhaps to prevent some of these cross-site scripting vulnerabilities. And then this was done via HTTP response headers. This is being done with these response headers. So these are the ones that we're going to cover. These things are difficult to get right, and it's very slow in adoption. You'll see that the percentage of sites that have some of these things is sort of like 10 to 20% have applied some of these headers. But if you connect to Google or Facebook and you see the headers that come back from these sites, they're doing it. So they're pushing a lot of the usage of these things. The first one is the easiest one, is the X-XSS-Protection. When you look at HTTP headers, the first part of a header, if it says X dash, it means experimental, meaning that it should be replaced eventually with a real header. So this is experimental, but it's still being used, even though something has superseded it. So this is why I'm going to talk about it. This is a server-specified response header that tells the browser to look out for cross-site scripting vulnerabilities, to look out for pages that when I send some input one direction, I get that same input back. Because that's the reflected cross-site scripting attack. I bounce some malicious JavaScript off of a site that ends up executing on the victim's browser as JavaScript. Okay? So this ensures that the reflected XSS is caught by the browser, So if Google sends this, so that Google does send this header back, but actually they send this out back disabled though, so I don't know what that means. Maybe they're confident they don't have any XSS on their site. The header values are these four. The first one is 0, which means the filtering is off. Yeah, don't check. And a lot of our sites, a lot of your exercises will hopefully not set this because you have to be able to do your homework. So the filter is off on these things. 1 means that you do the filtering and you just remove any code that comes back to you mirrored. So if you see the script tag going there and you see it coming back, all you do is delete it. Delete the stuff that is the same. The next one is to block the entire page. So again, if your post or your get has HTML, has content that comes back in the response directly, this would basically not render the entire page. So in the other one, you just delete the thing that comes back to you, but then here you just say, no, I'm going to trash the entire page. And then the last one is not only do you remove the content, but you actually hit this URL to report it. So this allows you to notify. So hopefully this is some route on your site that you monitor, so that when you start getting hits on this URL, you know that something on your site is vulnerable to a cross-site scripting attack. So this is actually quite useful. The report URIs are useful in detecting when your site has been getting hit by these exploits. The next set of headers is the content security policy. And this set of headers is sort of subsuming a lot of the other different protection mechanisms. The idea of CSP is to unify control over all content, not just the scripts, but the CSS files, the images, any sort of content that the page has. You want to apply a security policy across all of the content on a page, not just the JavaScript. So that's what CSP is. Let's see, what do I have here? So this is the header, HTTP response header. And you'll see that CSP is often essential to lock down really sensitive sites. So banks will use this. Obviously, popular web properties will use CSP. And it gives you more of an assurance that the browser is going to do the right thing when it gets content. You can test any website's CSP policy using this site, and it will scan the policy to make sure that it's reasonable. This is what the CSP directive entails. It allows you to specify first all the different content types you want to lock down. So you can see the default is everything, like it applies to all content. And then you can drill down to scripts, CSS files, embedded images. You can specify which sites AJAX is allowed to contact on your page. The different fonts you can use, the different media files that you can access, like where's the source of these media files, and then whether or not you're allowing iframes on your site, which we'll talk about this next class when we do click checking. As part of the header, so you start with this, you'll say, hey, I want to specify a particular policy. The policy is for one of these content types. And the value I want to associate with that content type is the locations that that content is allowed to be delivered from. So in this case, if I put a star, that means I can allow everything. I can completely disable the same origin policy, right? So if I did default source star, this is like, I don't care about security at all. So I'm sure the observatory is sitting there scanning sites and saying, hey, default source star, you get an F. I think that one does give you a letter grade in terms of your security policy. None says that page isn't allowed to access anything. Just shut, everything is embedded in that page, don't allow it to do anything else. The same origin policy is specified with self. So if I do a default source is equal to self, that's same origin. Okay. There are other ones. Data means allow inline data to be delivered in the page. If you want to open up your policy to specific domains, so you have a whitelist of other domains that you want to allow access across, then you could actually just enumerate those sites in a space-delimited sort of list. Allowing dynamic code evaluation via JavaScript with the unsafe eval. This seems like a bad idea, but it's there. And then, well, I think this is there for legacy purposes. Like if you have a site that does rely on that, then yeah, you're gonna set that, I guess, rather than re-implement the thing. Okay, so here's an example of a policy. So again, this is an HTTP response header that says the server wants to specify the content policy on the client. So default source is none, script source is self. So this is like deny all first. I apply the deny first, and then I say explicitly allow scripts from yourself. So this is same origin on scripts, same origin on AJAX requests, and then same origin on the embedded images, and same origin on the CSS. So that's effectively mostly same origin being applied to that page. Other questions about what's going on here? Yeah. Does each browser implement a policy in their own way? They must implement CSP in the standard way. Like this needs to be the same on Chrome and on Firefox, but it's the content provider, it's the website that specifies the policy. So the website is generated, so I run a website and say I want same origin, then I would configure my web server to give this policy back as an HTTP response header, so that when someone hits my index page, I have pre-configured this policy to be shipped back along with that page, so that that page now has very strict policies governing its access outside of my domain. Yeah, but it's the intent that the browsers will faithfully implement these policies as specified in the standard. So this is a web standard that is out there. Here's another example. Say you have a site that basically has embedded JavaScripts, not only on your site, but if you are using a content distribution network, so like AWS has their CloudFront, and the idea is that you want to be able to get your content really fast, so I'm going to push your content to the edge. I'm going to have a content server in Portland deliver you that script because I don't want you to have to go to the origin. And as part of that, the content server might be delivered from a CDN, a content distribution network. So like Akamai, for example, is a CDN. So then you might need to allow scripts that are included from Akamai as part of your policy. And so the way you do this is here. So script source, if I want to go all the way back to the origin, that's fine. But if I know that my script is hosted by Akamai, this could be akamai-cdn.com, star.akamai-cdn.com, and that will allow me to also get scripts from the CDN. It's just an example. Here's another one. Same thing, but also apply the same origin to everything else beyond just the scripts. So fonts, style sheets, images. And that's via specifying this to be self first. Here's another one. If you have a site that is using all of the different Google API services for site management and analytics and ad insertion, then you would want your site to be able to include scripts from Google, right? Like in order for them to implement a dashboard of data access to your site, you have to allow Google Analytics to run on your page. So you can see these things, like there's libraries of these things. Like Google will ask you to insert that as a content security policy in order to get all of the analytics working on their site. Okay, questions about that? So how do you configure this? You could configure this site-wide in your server configuration. So if you're running Apache, there's a directive in your virtual host that says, for this virtual host, this is the policy. Or Nginx has got a similar thing, which is like, here, add this header on all the responses, content security policy, and this does the same origin policy shipped back. You could do this on an individual page basis. So again, developers can modify the headers going back. So Node.js, Python Flask, all of these frameworks have the ability to send back custom response headers. So you could also include this in the HTML itself. So if your page generates the meta tags in the head field of your HTML, you can say, you know what, I'm going to say specify this content security policy in HTML, and then when that document gets shipped back, it will automatically assume that policy. There's just different ways of specifying the policy on the server side. Okay, so something like this in your HTML would then send back something like this in the header script source self. Okay, the last countermeasure I'm going to talk about, and I'm going to talk about it here because this is also something that you supply in the content security policy header. There's this idea, and this is proposed. I don't think this has been standardized yet, but the idea here is trusted types. So you see this a lot of these things that need input validation. Well, why don't I put a strong type system on top of that in order to make sure that the input is what I think it should be? That's the idea of trusted types. But in HTML, you don't have this notion of strongly typed things. Like, there's no type system for HTML. So the idea of trusted types is to try and emulate this. And the idea is to stop these DOM XSS attacks where you're doing something like this. So here's an example of a script that takes from the URI some field which specifies a template ID. So say you have a site that the user can set the sort of the look and feel of your site using a template ID, and then you can get multiple sort of looks and feels for your base page. Say it's implemented using this template ID, and then in order to implement this, you say, you know, based on the ID that you provide, I'm going to parse this thing, create this, get this template ID field, and then I'm going to include as the style sheet in my template directory a template ID /style.css. So this is the way that it was intended to operate, that you would get your template ID and then it would specify the different style, this different style file that you would get. But this particular mechanism allows the attacker to specify a template ID that terminates this HTML and then executes regular tags, regular HTML, inject regular HTML in this template ID. And so in this case, you're basically executing JavaScript on error. When you specify the image to be a bogus source and then register JavaScript that says on error, do an alert, this allows you to inject JavaScript into this template ID without even using the script tag, assuming that the greater than and the less than have been filtered out. Okay. Anyone see how this is working? Because we're trying to get rid of this using these trusted types. So the proposed trusted types approach is to define policies that must be applied at all of the different injection points. Any place where you think you can get cross-site scripts injected or HTML injected, you would want to put a trusted type policy that would say, this is what the content should look like before I produce that HTML. So in this case, I create this template policy, and this template policy, given that template ID that I'm parsing from the user, I'm going to make sure that the template ID conforms. So I'm going to test this template ID against this regex. And so it must begin and end with characters that are all digits or lowercase letters. Okay, so that's the idea. And then if it does match this, I am then going to emit the HTML that selects that template. Otherwise, I'm going to throw a type error. And this will cause the whole thing to stop, right? As soon as someone injects something that doesn't match the template format, it just crashes, okay? And so then at the injection point, I have this HTML that says I'm going to call the policy to create the HTML on whatever the thing is I parse. And if that thing returns, I'm just going to attach that HTML to the regular page and then be done. The problem is that you have to make sure you get rid of all of the insecure ways of doing this. And so that's what Trusted Types is doing. It enforces the use of policies at all injection points underneath so that something like this, where this is the insecure method, this will automatically throw a type error because you're not using the Trusted Types policy to append the HTML with this. So this is a type mismatch because the Trusted Type system wants to make sure this is a sort of a trusted HTML type before appending it to that thing. So this is just an example of how types and more strongly typed systems are being used to validate the content being appended. Okay, so the way you turn this stuff on is through this content security policy header that says, enable trusted types. And then when the cross-site scripting attempt is issued and someone clicks on this, you'll see that this regex will fail. And then you'll get a type error as a result of that access rather than the actual attack. Okay, questions about trusted types? Nope, stretching. Okay, the last thing I want to talk about today is CORS, cross-origin resource sharing, and I actually have a lab on CORS. It's a relatively simple one. Okay, so this is an alternate method to CSP. This actually precedes CSP, but it's a way of explicitly allowing two related sites to share content with each other. So here's an example of FB.com and Facebook and Instagram. Because they're owned by the same company and they want to integrate the users with each other, it is often the case that a Facebook script a Facebook page wants to inject a script that accesses Instagram content. Okay, so in particular, if you have accounts on both, you'll see that what Facebook wants to do is that if you're connected with certain people on Facebook, they want to show you on Instagram that you have connected on Facebook, right? So that you can make a connection on Instagram. So in order to do this, when you visit Instagram, Instagram needs to be able to run a script that accesses your data on Facebook. And this is disallowed with the same origin policy. And so this was the problem they wanted to solve. But if you allow this kind of sharing, you could potentially have the Instagram user visiting malicious.com and then having malicious.com pull all the contacts that you have on Instagram.com. So you want to allow Facebook access, but you want to disallow malicious.com. And this is what CORS is intending to allow you to do. So here's an example. So in the blue is Facebook, and on the blue is Instagram, and on the red is Facebook. So you're interacting with this origin page, and then you want to be able to render canvases or run scripts that get access to the other site. And these are called cross-origin requests because you're crossing origins from domain A over to domain B. Okay, so the way this is done is with two headers. The first is a request header, and this is the origin header, and this header gets set by your web browser. Your web browser knows what page you're on, and so when you go and you access some content on a site, you will say, well, this is sort of like a referrer. What is the origin domain that I'm on? The other header is access control allow origin. This allows a website to say what other domains can access me, cross-domain. So that's the header. So this specifies the domains that are allowed to access your site cross-domain. If you have this set to star, which this reminds me of the certificate thing totally. You're like, God, this thing doesn't work. I'll just turn this into a star and it'll definitely work because the whole thing will be disabled. There'll be no policy applied, and so you'll be able to get this thing to work. If you do specify sort of a domain, then basically it's going to use the site, the port, and the protocol, just like before. The JavaScript same origin policy would do. It would match against all of those to allow particular accesses from particular origins. Okay. One of the things with CORS is that it explicitly, by default, doesn't allow the use of cookies on that cross-origin request. It's like, okay, you're not going to be using, like, if you're trying to get access Instagram from Facebook and vice versa, we're not going to allow you to transmit the cookie as part of that to make it an authenticated request, but you can disable this. So again, this is the XKCD thing. I actually do want to supply credentials, so the script can set the with credentials flag as part of this header to say, yeah, allow the credentials to be sent while you're accessing me as well. And that's what this is there for. Okay. So that's actually a separate header. So allow access control allow origin and access control allow credentials are separate headers. Okay, so here's an example of how it works. You want to allow Instagram.com data from Facebook.com, but disallow access from malicious.com. So your browser visits Facebook. Within Facebook, it gets this thing that, oh, you know what, send a request to Instagram.com for the contacts, for example. The browser says, I'm going to access Instagram. The origin is Facebook. And then as part of the response, Instagram says, you know what, you can allow this cross-origin request only if you're on Facebook.com. And of course, the browser's like, I am on Facebook.com. This is all good. Then it will basically allow full access on that page. And then you would implement that UI that you saw earlier. That's how it's intended to be used. And then if you're a malicious site and you trick the browser into visiting you, and you say get Instagram.com, just like before, the origin is malicious.com, and then because the response header has an allow origin that doesn't match, then you would basically give no access. Okay? Questions about CORS? Relatively simple mechanism, but oftentimes done very poorly, as it turns out, which is what your homework is going to be. There's only one homework. Here's an example of it being done poorly. This is a digital wallet that holds a bunch of Bitcoin. It had a local JSON interface. And so the issue with this was that the victim can hit a malicious page that had a CORS policy that was misconfigured. And the way it was misconfigured is exactly the way your lab, there's only one exercise for CORS in your lab assignment. And basically, a lot of policies will take your origin and then echo it back on the access control allow origin response. So it's basically the same as star, allowing everything to echo the thing back. That's what this thing was doing. And then this basically coughed up, was potentially allowing people to cough up the private keys of all of these wallets. So just to give you an example of this being CORS, misconfigured CORS being a thing. So this happened a couple years ago. Okay, so now I'm going to talk about the labs and the homework. There are a sequence of cross-site scripting labs in Web for Pentester 1, and then a game that has been implemented, 6 levels, and every time you solve one level, you get to the next one. So this is, I really like the game, so I put that in there. So that's the first code lab. There's the second code lab gives you some experience with these headers. So what you'll be doing is that you'll be running Node.js, with a sample server that will allow you to twiddle with the headers and then see the result of what these headers are doing. Okay, and then the last part is there's a single level. The initial cores level on Portswigger is the last. So here is the first server. You're going to run two different servers, Node.js servers. One is to set the XSS-Protection header, and you can see that this server is pretty trivial. What it does is that it echoes the header, so it takes the URL parameter XSS, and then it echoes it back as the response header. And so what you will do is that you'll say, and this thing just delivers HTML, and it delivers HTML back to the user directly. So it'll take your user parameter. There's two parameters here. There's the XSS parameter and the user parameter. And the idea is that if you're not doing any sanitization, your user could be like alert hi, or script document.cookie. And so the XSS field is going to set the header, and then you're going to see whether or not the echoing is going to happen. So you're going to inject as the user field all sorts of different payloads to see if cross-site scripting has been filtered out. And so you're going to use all four settings of this header, the 0, the 1 mode block, and then the 1 mode report as part of this server. So that's the first one. So here, I'll walk through the code. So this is a Node.js server. It uses Express, which is the web server part of Node.js. So this line creates the server, and then this will register a request response thing that says take from the request the XSS field of the URL parameter, and then set the response header to whatever that thing has, and then as a response send this HTML that will echo whatever the user parameter is, otherwise say anonymous, and then this thing just listens on that port. So this is just a trivial Node.js server that you'll run. The Content Security Policy Lab has a similar server. This is a demo script that will allow you to set the policy across 3 different ways of downloading a JavaScript. Similar to the previous one, it's got this CSP parameter that sets the kind of policy you want to test out. So this is the code for that. And again, the first thing is it creates 2 servers. And it creates 2 servers, one on port 1234 and one on port 4321. So what we want to do is test whether or not cross-site scripts work. And so we need 2 servers because we're going to download the page on one port, and we're going to try and include a script or content from the other server. So that's why we're creating these 2 servers. The next thing is that to implement a cross-site script, we're going to host a file called script.js. And the way this file is hosted is it's actually hosted in code directly in line. So anytime you access this URI, it actually doesn't get a file in the file system. It just returns back a piece of JavaScript that changes the inner HTML of whatever query ID you supplied to say you were changed by me. Okay? So this is going to be used as the remote script. Okay? Then I am going to, this is the main server. I am going to, on this server, set the content security policy header to whatever the user supplies. And so this is the experimental part. You'll be trying different kinds of headers. And then I'm going to send back this HTML. And this HTML is going to have 3 DOM elements. One that says an inline script changes me. One that says the same origin script is going to change me. And then one that says a remote script is going to change me. And you'll see right here, this is an inline script that is attempting to change the inline element. And then this is a script that accesses the JavaScript route using the same origin. And so it will pull this, oh God. Well, hopefully, it's not much that's missing. It will pull this script and then try and change that element using the same origin, from the same origin. So it'll retrieve it on 1, 2, 3, 4. If you access this page on 1, 2, 3, 4, this particular thing will try and get on the same 1, 2, 3, 4 port the script, and then it will say try and set the origin element, the same origin element, to be changed. And then finally, this is the cross domain where you're accessing it on the other port. Oh, so actually this is meant to be hosted on 4321, and then the third element is going to access it as a remote cross-site script. And then what you're going to do is different CSP policies are going to shut down different parts of these, just to show you how it works. So that is the CSP lab. And I just wanted to, because when you run code, I like for people to sort of understand the code that they're running, so that's why I wanted to walk through this particular piece of code. Okay, the homework, the lessons, and then the challenges 1 through 5, and then I'll stop there. Are there any questions about cross-site scripts? Okay, just gonna take attendance.